Sì, sì, ce l'ho fatta. Go, go.
Okay.
Fine.
So, okay, I take back from where I left in episode 1. So what we have seen in episode 1 was, well, a pretty, well, let's say, maybe not so easy to follow construction of the Berezinian in particular, using a homological algebra through a generalization of the Koszul complex for superalgebras and super modules in particular. So in this, let's say, episode 2, we will actually use this. Hi,
Emanuele. I forgot about Emanuele, but he's joined us. Yeah.
Okay. So in episode 2, we will use this construction, and finally, well, hopefully you will get to see some more geometry compared to the algebra of episode 1. And the aim of this episode number 2 is to provide you with a, well, let's say a sort of a unified construction of notion of two, well, seemingly different notion, which are the notion of differential and integral form. And I'll discuss the cohomology of differential and integral form. And if time permits, some loose hands on integration. And I'll try to make contact within the, well, let's say the shift theoretical formalism, which I'll use in this talk, and the, let's say Grassi-Cremonini formalism that you have seen in some previous talk, for example, by Carlo. All right, so I'm gonna start with something that you guys all know. So
Antonio, last time I regret he could not ask a question. So Antonio,
yeah, indeed.
We want to hear your questions and Simone's answer, okay?
Yeah, sure. Indeed, I have a part at the end of the talk where we can actually, you know, discuss about this and also argue about things we do not agree on. Okay. All right. I'm gonna start with something you guys all know. So the Derham complex. So if we let M to be a smooth super manifold, so the main thing to know over here is that the Derham differential, which is a map from the structure sheaf of the super manifold to the sheaf of one form, is actually an odd derivation. So it is an odd derivation. So this means that it turns, in particular, like even section of the structure sheaf into odd section, and odd section into even section. So this has a far-reaching consequence. This very easy fact has a far-reaching consequence, which is that the Derham complex over a supermanifold is not actually bounded from above. So it goes up and up to infinity over here. So some remarks. So the first one is that you can see that there is no notion of a top form inside the Derham complex over a super manifold. And also you can see that the Berezinian does not sit in the Derham complex. So a little nod to relation with the integration theory. So it turns out that the section of a sheaf that you can find inside Derham complex can only be integrated over ordinary submanifold. So submanifold of codimension K/Q inside the supermanifold M. So in other, to say this in a different way, differential forms are really not the right object to look at if you look for an integration theory on supermanifold.
Simone, sorry, can I ask you a question on the previous slide? I'm sorry about that. So I'm sorry, you were kind of fast. I didn't catch how you can be sure that the Brazilian is not in the RAM complex. So this trivial thing, I don't see it.
Yes, the point is that the sheaves that appear in the RAM complex are only sheaves. Well, you can see these sheaves as the keyfold tensor product. So, well, say omega km is the keyfold tensor product of the parity shift of the dual of the parity shift tangent bundle. Okay, so this guy will be generated by some, well, let's say some section which will be the key forms, which in turns will be given in terms of a certain like combination of one forms. But we have discovered in the previous talk in episode 1 that the Berzinian is not such a thing. So the Berzinian, it is actually not generated by an expression like this. So there is, well, you can actually look inside every sheaf like this, and you discover that you're not gonna find anything which can actually generate the Berzinian. So these are just forms, whilst the Berzinian is not really differential forms. It's actually something different. So in other words, you cannot find any elements inside here that transform as the Berzinian.
Okay, thank you.
So this is a very concrete way to see this. Another way is that, well, yeah, for example, you can also actually also say that no sheaf like this appears from the cohomology of the Koszul complex. So necessarily the Berzinian is going to be something different. But yeah, it's pretty much the same thing. Actually, you know, the point is really that you don't find any, if you look at the generator, so if you look at locally, you're not going to find anything inside the sheaves that transforms like a Berzinian, okay? So the Berzinian is really something, well, you can say that it's really something irreducible, but doesn't sit inside here. It is a natural sheaf defined on a supermanifold, but it doesn't really sit inside here. So the idea that I would like to convey here is that if you look for integration, so if you think about forms as something you can actually integrate over a super manifold, differential forms are not really the right object to look at, because basically you realize that you can only integrate differential forms on the downstairs reduced space. So you cannot really integrate differential forms over the full super manifold. So in other words, turns out that you really need to look for something different if you want that your odd direction to be really part of the integration process. And for example, well, this is actually crucial in terms of, for example, with an eye to physics, writing action on superspaces. So in other words, if you are interested into having your, well, supersymmetry to be, well, built in a sense. So this is related with something different. So not really differential forms, but actually something different. So this is actually related with what have been called integral forms. So in this talk, at least in the first part of this talk, then I'll try to make a connection. Integral form, in particular an integral form of degree p minus k, is just a section of this tensor product over the structure sheaf of the supermanifold of the Berzinian of M with the, well, say, keyfold supersymmetric product of the parity sheaf, the tangent sheaf, okay? So the Berzinian sheaf is exactly the guy that I try to introduce and define, basically define in episode 1, because yeah, pretty much the whole episode 1 was about the definition of this, say, Hod sheaf over here. where by odd I mean strange, not referring to the Z grading, of course. So again, what is the ski-fold supersymmetric product of the parity parity shift tangent shift? So this guy, well, if you look, for example, at pi Tm, this guy is the true dual of the shift of one forms. Why I need to take the parity shift? Well, because I look at the dx as an odd quantity, because the de Rham differential is actually an odd morphism. And likewise, I look at the d theta as an even quantity. So the dual of the dx will be an odd quantity, and I define it pi derivative with respect to the x, and the dual of the d theta will be pi the derivative with respect to the theta, and this guy will be even. Okay. All right. So the interesting thing about integral form is that actually they're structured into a complex. How does this complex look like? So whereas we've seen that the complex,
Simone, sorry, can you go back for a second? You are really fast, for me at least. So I'm slightly confused. So the Berezinian sheaf of M, right, is somehow, I think of it as the top form. Is the for me is like the equivalent of a top form for a regular manifold, right?
Yes.
And now you add something to it.
Yes, exactly. So I'm not really adding something to it, because if you, for example, if you look at this slide,
yes,
you can see that if you choose, well, for example, k to be 0, you actually only have the Berezinian, which sits here, okay? So in a way, you can look at this complex like a complex where the Berezinian is actually truly a top form in some sense.
No, but the thing I'm asking is that wouldn't you get a 0 if you integrate on a form that is not the top form, right?
Yeah, I mean, the problem is that you might want to integrate, for example, on the full supermanifold, and then you look here, but maybe you want to integrate over for example, a codimension 1/0 subsupermanifold, and then you look here, and back and back and back. So
I see.
Yeah, I'm gonna say a few words about this, and later on I'm gonna show you some example.
No, don't say a few words, say more than few words, because that's an important point to me.
Yeah, well, actually, you know, the aim of the first part of the talk would be to discuss, let's say, the homological foundation of this guy over here. So this is not going to be, well, let's say the first part is not going to be on the application of this kind of a theory, but better on the foundation of the theory. So it's not really about, you know, what are these things good for, but better where these things come from, or you know, something like that is a really, you know, foundational point of view. But anyway, I'll try to second this. So let me just tell you that a pretty, you know, a pretty bad thing over here is that if you look up on the literature from the Russian school, so this integral form has been first defined within the Russian school in the 80s, which studied supergeometry from, well, let's say an algebraic geometrical point of view. You discover that differential that they introduce is actually something quite complicated. I don't want you to lose your eyesight on this, but just observe that this guy, well, it's pretty cumbersome. It's pretty complicated. Okay, So I'll try to make it more natural in some sense. So, okay, this in a sense is exactly what I said early on. So you can integrate, it turns out that you can integrate section of the Berzinian over the full supermanifold M, section of this, well, let's say integral form of degree pi p minus 1 over a sub-supermanifold of codimension 1/0, etc., etc. So any question? Okay, so all right. A remark here is that you keep the odd codimension freeze to 0. In other words, basically, when you integrate over this guy, over this integral form, basically you freeze all the odd codimension, all the odd dimension, and you integrate out all the odd dimension, okay? So you don't move inside the odd codimension here. All right, so some pros and cons. So you might say that integral form seems in a way more useful and natural if you want that a form to have some sort of a, relation with okay. But on the other hand, with respect to differential forms, turns out that they are rather complicated objects, complicated items. So also homologically, they're differential if compared with the de Rham differential is actually pretty bad, pretty cumbersome. So some issues are therefore lurking out. So for example, there exists a construction. Is there a construction which in a way relate differential and integral forms, and well, in some sense tells how similar or how different are differential with respect to integral forms, and also which kind of invariants related to a superspace differential and integral forms do actually compute. So in the next slide, I'll try to address some of this question, and I'll try to give you some answers using so-called universal de Rham complex and universal Spencer complex. And the trick here would be to actually unify these two complexes into a single double complex. So something I really care of is so-called naturality. So what do I mean by naturality? So in a very, in some sense, naturality means that I don't want to make any choices. So I want my construction to be as natural as I can. And I would like only to I would only like to use natural sheaves, so sheaves that can be naturally defined over some space, over some geometric space, such as, for example, the tangent sheaf, the dual of the tangent sheaf, sheaf of endomorphism or orthomorphism of some structure related to a space, and also as the sheaf of differential operator over a certain space. So this sheaf, which is usually called dm by differential, is just a subsheaf of the sheaf of endomorphism of the structure sheaf of the space. And in particular is a subsheaf which is generated by OM, so the structure sheaf itself, and TM, so the tangent sheaf. And well, if you look at this guy locally, you discover that it actually looks like, well, not really a Weyl algebra, actually a Weyl superalgebra. So locally, it is the generating section, which comes from the structure sheaf and from the tangent sheaf, are actually characterized by this commutation, by this relation over here. So clearly, crucial relation over here is this one, which tells you that you have this, say, commutation or anti-commutation relation, which makes this sheaf dm into a sheaf, into a non-commutative sheaf. Okay, and well, you can expect, well, you can clearly expect something like that, because an operator, differential operator, is not in general commutative. Okay, if you have a sheaf like this, so a sheaf of differential operator, you can think about an action of this sheaf over another sheaf. So in this case, you have what is usually called a left or right D module. So observe that you really need to specify whether you have a left or right D module structure, because your sheaf dm is non-commutative. So the order of the section is actually important, and usually left D module is not a right D module, and vice versa. So this really makes a difference over here. In a way, we are actually, moving a step inside non-commutative world better than supercommutative. So this guy has a non-commutative structure, but also supercommutative structure. Okay, so now I'm using this sheaf to define another construction, which I call universal de Rham sheaf. And this is nothing but the tensor product of, well, let's say the de Rham complex with dm. So you have forms and differential operators over here, okay? It turns out that you have a natural operator that acts non-trivially on this tensor product of sheaf, and this natural operator look like this. It is the sum of two bits. Here you only have the de Rham differential, which clearly acts on the first of the first item inside this tensor product. And here you simply have, well, basically the multiplication by a form like this and a derivation like this, which clearly goes on the D module over here, okay? So what are the properties of this operator D? Well, I say that D is a natural operator, so what does it mean?
So,
well,
Simone,
first of all,
sorry, can you go back for a moment? So
Sure.
I'm a bit confused, I apologize about this. So you are making a choice of coordinates, aren't you? I mean, I'm confused.
Exactly, but see the first property here.
Okay. Okay, so you define it locally.
Exactly, exactly. But it turns out that it is actually invariant. So if you go for a generic diffeomorphism of your manifold, of your super manifold, this operator here stay the same, exactly the same. And I mean, you can tell why, because clearly D is invariant. But
no, I can tell why. I was wondering if it was a less cumbersome definition, that's all.
Well, in some sense, you can tell that this guy over here is a multiplication by, in a sense,
like Euler, no?
Well, not really. It's better, well, let's say symplectic form or something like this.
Oh, okay. Sorry about that. Okay.
Yeah, no problem, no problem. But you have to provide with the right interpretation of this. So, I mean, I prefer to write it in this way because, I mean, if you say, oh, this is like a symplectic form or something like that, well, then I have to well, specify other structure, and it looks like I'm living somewhere else, I'm doing somewhere else. While over here, I'm writing like this because I would like to go as general as possible, so not introducing further structure. Okay, so all right, so the second definition, sorry, the second property here is well, let's say a technical one, but actually a crucial one. It simply means that since the product, this tensor product, was over OM, I'm actually free to move a function from one side to the other side of the tensor product, and the effect of my operator is not going to change. The crucial property here is the third one, which tells that I'm dealing with a homological operator. So the operator is actually nilpotent. This turns my de Rham sheaf into an actual complex. So the grading of the complex is inside the omega here, and you can tell that this operator D raised the degree inside omega by 1, because well, this clearly raised by 1 by definition of D, and here I have a multiplication by the X, which also raised by 1. All right, so I have a complex, and I can compute the homology of the complex with respect to this operator D. So the homology of the complex, clearly this is a complex of sheaf. So I expect the homology of the complex of these sheaves with respect to an operator, which is a morphism of sheaf, will be a sheaf. And it turns out that the homology is precisely the Berezinian of the super manifold M, okay? So I'm not gonna give the proof of this fact, but I just want to observe that the proof, I just want to, well, in a way, say why it is actually important to have
but Simone, you lost me. Go back. Yes, so Berezinian is a sheaf.
Yeah.
Now, this homology is giving you a family of objects, right? So how can you identify with the sheaf? I'm very confused.
Well, you started from a complex of sheaves, and you're computing the homology with respect to a morphism of sheaves, right?
Yeah, I must be confused. I even studied, I even prepared. But the Berezinian, I thought it was a sheep, the Berezinian.
Sure.
Ah,
sure,
no.
Indeed.
You look at it, I see.
This is all the thing that you're actually looking inside these slides are actually sheaves or maps of sheaves.
But there is a bullet. It means that you have a family of, right?
This simply means that I'm taking the homology.
Yes.
No. Okay. Oh, okay. Sorry. Well, this is just. Oh, okay. I got what you mean. This is just well. Say that instead of seeing H bullet, say HD, which means that the homology with respect to D. So I'm not gonna get a complex. I'm getting a sheaf out of this homology computation. So instead of H bullet, say HD. So sorry.
What is D?
Is the homological operator?
No. Yeah, but they say HD. D. You are looking at a special homology group. Which one? No, but you have H bullet. It's all of them.
Yeah,
right?
Sure, exactly. So this is actually concentrated in a single degree inside this guy over here. Okay. And in particular, this is going to be concentrated inside here, which is where you have the grading in degree P, where P is the dimension of the super, is the even dimension of the super manifold. Okay. But I'm actually writing like this because, well, this is going to be a little bit misleading if I write P. because it turns out I have a sheaf. So in general, you write this guy like this by, well, this bullet over here is not really say necessary, and it can actually be a little bit misleading.
What degree is the Berezinian?
Well, inside this, it should be in degree P if the grading is given by this.
Well, I think that you are missing the degree of the fermionic degree. I mean,
no.
Yeah, in this way, yes.
No.
Of course, yeah.
Because I say that the homotopy. Sorry, because
no, I think you have also gradings on the D model. You also have the grading there. I mean, why you have? Of course, yes.
No.
But the Berezinian.
I only have the degree. I do not have any. I do not have any grading on the D module unless I look at. Unless I'm taking the graded version of the D module, which is just the direct sum of the tangent bundle. But in general, I don't have like a grading there.
But yeah, but where is the Berezinian?
Roberto, anche te.
Can I just press a little bit on this?
Yeah, sure.
So you have a complex of sheaves.
Yeah.
You take the kernel sheaf mod the image sheaf.
Yeah, exactly.
Is that right? And then you sheafify again, right? Because that doesn't need to be that's a quotient operation, so it doesn't need to be a sheaf.
Yeah, but sorry, what was the question again?
I mean, so like when you have a complex of sheaves, then if you look at the kernel of some map,
sure. Okay.
If you look at the kernel of your differential, then that's automatically a sheaf.
Yeah, sure.
That's just a limit, and that commutes.
Yeah, exactly. Yeah, right. That's totally true. Okay, so
the image is not necessarily a sheaf.
Sure, exactly.
So you have to sheaf. So what the image means is that you sheafify.
Exactly. So if you want, you can say that this is the sheafification of what I get out of this. But it turns out that this is actually a sheaf.
So it's already a sheaf. You don't have to sheafify. And
Exactly.
that's because of like existence of partitions of unity, or you're not assuming
that? No, this actually holds true in any category.
Okay.
Let's say any geometric category. And so smooth supermanifold, complex supermanifold, but also algebraic supermanifold. And this is, for example, this is actually related to the fact that the homotopy that you happen to find is actually algebraic. So it doesn't involve any integral, for example. And you can actually also live in a algebraic category over here. So the point that I want to make here was that it actually turns out the homotopy that you find over here, so fail on an expression like this. So
wait, I have some questions. Sorry. I mean, I don't understand. I mean, it is related to Rita's questions. What is this bullet?
What? Sorry.
Okay, the bullet in the previous formula.
Okay. Just
you have the bullet there. Okay.
So if you want, you can drop this bullet.
No, I don't want to drop it. I mean, I want to understand it. Okay, what is this bullet?
It's a symbol for say a cohomology.
Yes, okay.
Or homology, if you want.
You say that the cohomology is concentrated on a specific cohomology group or homology group, whatever, okay? And what is this cohomology group? Which is the grading of this?
Well, if you look at this, sorry. Here, you live in degree P.
Why? I mean, P and Q. Why P only? P and Q.
Because I'm not assigning any degree inside here.
So is dimension PQ? Is that the M? The dimension of M is PQ? Is that right?
Yeah, right.
Yeah,
Just
exactly.
Just checking.
So you need also the Q.
No, because I'm not putting any degree over here.
Well,
so
okay,
this,
so then I don't understand why you get only the P on the ballot.
why?
So, well,
Because this is the only degree that I have here.
I don't get it. Okay.
Because the degree, well, if you want, this operator to me raise the degree over here. Okay. So my degree is only over this guy, over this Durham complex here.
So where is it? Where is the Berezinian sitting then?
In degree P.
Why?
Here.
Why
Because
not P and Q?
Because the expression that I find at the end of the day is something like this. So
Well,
I have
but then you get
P.
the Q also there. So you get, you see
Exactly, but here, but this element over here, it does not belong to any degree with respect to the complex that I have actually defined here.
Right, script D doesn't have a grading, right?
Exactly.
Yeah, exactly.
There's a Z mod 2 grading, but not a Z grading.
Exactly. It's Z mod 2 grading, but not Z grading, not Z graded. So in general, if you have a sheaf of D module, so sorry.
No, I don't agree.
got it
I
wrong.
don't agree with that. I mean, you have a,
If
you have a Q theta, so you have also a degree Q on them, of course.
No, I'm saying that in general, so a sheaf of differential operator does not have a Z grading. So if you take the filtration, or if you evaluate these on an open set, well, then you get a Z grading, because this splits into a direct sum of symmetric product of tangent sheaf. But in general, the M does not have any Z grading.
No, maybe you can go ahead and then we discuss in the end. How about that?
As you prefer, yeah, sure. But
on this topic, yeah.
Okay. All right. So what I like, well, let's say a thing I like about this theorem is that it actually yields pretty much for free a right action of dm on this homology class, let's say, which is actually the Berezinian, which is uniquely characterized by this, say, this condition over here that you see in the slides. And it turns out that this is really what we call the Lie derivative on the Berezinian. So Lie derivative on the Berezinian, well, basically, it's something that goes like this. Okay, the Lie derivative, for example, on a generating section of the Berezinian with respect to a coordinate vector field, it's going to give you 0. Okay, and this is enough to actually define the Lie derivative. Okay, so let me expand a little bit on this. So as far as I know, well, I knew two construction of a Lie derivative on the Berezinian. So the first one was, let's say, analytic by a flow of a section along a certain vector field. And the second one, actually, Antonio explained to me how to do that, is basically generalizing a notion of Cartan calculus. But one should be a little bit careful about this because, well, this is actually, let's say, related to the issue of naturality that I raised early on. And yeah, I mean, when first you show me that this kind of computation, I was like, no way. But truth is that it actually worked. It's actually worked pretty well, and it's actually pretty effective. So all in all, if you go through this computation, you're gonna find explicitly something like this. which is quite bad. But if you allowed, well, let's say a right derivation, this gets better. So you're gonna find something like this, which looks better in a way. So you soak up all this bad sign over here. So in a way, this tells you that, you know, this looks a little bit more natural if you allowed like a right action or something like that. So let me go through this for a moment. So we have a very nice characterization of D modules. So left and right D module in terms of O module. So we have a fairly good control of O module. So D module are clearly a little bit subtler from the point of view of the, let's say, structure. And it turns out that, if, for example, right D module is nothing but a sheaf of O module together with a flat right connection. So the same is true for a left D module. So it's nothing but a sheaf of O module with a with a flat left connection. So the question here is clearly, okay, what is a right connection? So the defining axioms of a right connection are these, and in a way, their structure has to basically give a right action of a vector field on a certain section of the sheaf E over here. So if you go through them, I mean, they're not so important over here. So if you go through them and if you look at number 2 and number 3, you discover that number 2 and number 3 together gives you sort of a modified version of the Leibniz rule, which looks like this. Basically with a minus instead of a plus. And well, clearly, notion of the flatness is actually related with the, well, let's say the commutation of the connection with the operation of taking the commutator of vector field. So it's the usual flatness of a connection. All right. So do we know any flat right connection? Yes. So actually, everybody knows a flat right connection. So up to a sign, oh, sorry, I forgot a top over here. Anyway, up to a sign, a section of the canonical sheaf, or if you prefer, the determinant bundle of an ordinary manifold M, defines a flat right connection. So automatically, using this theorem, you see that the canonical sheaf, so the determinant bundle over an ordinary manifold M, is actually a right D module. So it turns out that the same, exactly the same, is true for a section of N, okay? So up to a sign, Lie derivative describe a flat right connection on the Berzinian sheaf. So again, you know, in a sense, a point of my first talk was about, well, let's say, see a similarity in terms of the structure between the canonical sheaf and the Berzinian sheaf. Again, here we see that the canonical sheaf and the Berzinian sheaf share another interesting property. So in particular, they're both right D module, okay? So we're in this situation. So over an ordinary manifold, so the canonical, in some sense, left and right D module sit in the same complex. So, well, okay, so which is the left D module here? Well, it's this one, is OM, is the structure sheaf, okay? So the flat left connection is given by D. It's nothing but that. Over a supermanifold, the situation is actually different, and I think a little bit more interesting. So canonical left D module and canonical right D module are the pivotal construction which belongs to two different complexes. So you have OM into the complex of inside the complex of differential forms, but you have the Berezinian inside the complex of integral form. Okay, so you see that there is actually different compared to ordinary manifold situation. Let me introduce some other construction. Early on, I've introduced so-called universal de Rham sheaf. Now I'm introducing what I'm calling the universal Spencer sheaf, which is similar to the universal de Rham sheaf, but this time I have the tensor product over OM of dm, which is again the sheaf of differential operator over the supermanifold M, and the dual of the de Rham complex. So this can also be denoted like this. So it's the this functor over here applied over the parity shifted tangent sheaf. Okay, so we have again an operator which acts on this sheaf. This operator is pretty nasty. Is really it's quite cumbersome, and basically it is made up of a contraction over here, and this operator E over here, which is a Lie derivative and a contraction. So from the point of view of degree, the degree is actually concentrated here. And you see that this operator lower the degree inside here, okay? Because you have a contraction of a, let's say a polyvector field and a form. So this operator is actually different compared to the other one, because basically the other one was made out of two bits, and each bit was basically invariant by itself. So this operator, this bit over here, the first bit is local operator, and the second bit is another local operator. So something actually magical happened, which is that all in all, the operator delta is actually globally defined. So all in all, it is invariant under generic change of coordinates. So, I mean, if it wasn't like this, it wouldn't make sense to, for example, think about clearly homology with respect to an operator which is not invariant under generic change of coordinates. And it makes sense to actually consider the homology with respect to this operator because this operator turns out to be nilpotent. So again, this is the crucial bit over here. So this is the theorem which mirror the computation for, let's say the universal de Rham complex. And again, you can discard this. This is just, a quotient if you want. And it turns out that now the homology spit out the structure sheaf of the supermanifold M. Again, the crucial point is actually to construct an homotopy, which is a very nice one this time. And this homotopy operator fails on function on OM. All right. So in other words, basically, out of two, out of the computation of homologies, we have found, in a way, the pivotal right D module for the complex of integral form, and the pivotal left D module for the complex of differential form. So how to relate this to construction? At this point, it's not hard. It's actually quite easy. because it is enough to consider the triple tensor product instead of just the, you know, this first pair of like tensor product over here, which I call the, well, let's say the universal de Rham complex, or this second pair of like tensor product over here, which I call the universal Spencer complex. Okay, I call this triple tensor product, it's just a name, sheaf of virtual superform. Okay, and how can I make this one into a bi-complex? Well, what really does the job is that if I extend the action of the operator D and delta in a trivial way, I get to commuting operator. So in turn, if I redefine one of these two, I can get a pair. This is just redefinition of the action of the second one. It's nothing strange. So I get a pair of anti-commuting operator, and in turn, I get a double complex. So this guy over here is actually a dibble complex. So the degree are here and here again. So attached to this double complex, I have two spectral sequences. I'm calling one E omega and the second one E sigma. So we'll see in a moment that this omega is actually related to differential form.
Excuse me, can you go just a moment back, D hat and
Sure.
delta hat? I just lost it. So D hat.
Yeah, I mean, this, sorry?
D hat and delta hat. Oh,
yeah,
are those? Okay, I see.
Yeah,
okay,
these are just a redefinition. This is really the same.
I see.
This is just a redefinition to make things actually work the way they should, basically.
Okay.
It's nothing crucial. It's really nothing.
So I mean,
important.
why don't you call it D hat is D times 1, right? D hat is the D tensor.
Sorry?
1.
Sorry?
D hat is D, the tensor.
Yeah, exactly. Well, in my mind, this should have eased a little bit the notation, but it's probably not like this.
Yeah,
but,
it confused me, but go ahead. Okay, fine. Okay.
All right. So I have two spectral sequences. So and oh, yeah, well, let's just jump to the computation of these two spectral sequences. So okay, I'm using this later on. So the first spectral sequence gives me differential forms at page 1. So why it gives me differential forms at page 1? Because basically I'm first acting with the operator, which was the operator delta, which actually yields me the structure sheaf, and I'm left with the de Rham complex tensor by the structure sheaf, which is again the de Rham complex, because the de Rham complex is is actually a complex of sheaf of O module. And at page 2, where the spectral sequence converge, I'm just getting the so-called constant sheaf valued in the field K, okay? Which in this case is R or C for a real or complex supermanifold. I have, well, the analog result for integral form. So if I consider the other spectral sequence, I get integral form at page 1. And I get again the constant sheaf valued in the field K at page 2. Okay, let me tell you something here, which is important, or at least for me, it is important. So the computation at page 1 holds true in any geometric category, so also for algebraic supermanifold. But the computation at page 2 hold true only for real supermanifold or complex supermanifold. So this does not hold true in the algebraic category. And yeah, for example, we can see in a moment why. This is actually, well, you can tell that the...
Because you don't have a global object for that, right?
Well, you know, the problem here is that, I mean, I'm working with sheaves. So, well, let's say that the problem stays into the Poincaré, so-called Poincaré lemma for integral form, for differential form, but also for integral form. So, if you want to compute this cohomology, well, the problem here is that the homotopy that you can write, for example, involves an integral. So you are, if you pretend you're actually working inside the algebraic category, as soon as you do this integral, you get spit out of your algebraic category. So this holds true only in the smooth and analytic. And well, let's say that by itself, the problem of, well, let's say an algebraic theorem theory is a very difficult one. So, I mean, also in the ordinary commutative setting for algebraic varieties, this is, well, quite an hard problem. So, well, actually, I'm not sure there's such a thing such as an algebraic Poincaré lemma or something like this. So I don't see how this can be generalized. But I confess that I'm quite ignorant about such an issues. Okay, so anyway, for example, for differential form, the homotopy looks like exactly the same as on an ordinary manifold. The interesting homotopy is that for integral form. So the homotopy is pretty weak. So you really need some, you really need to be careful in computation to prove that you have an homotopy, and that an homotopy which looks like this actually works with the suitable choice of QS over here. But anyways, it turns out that the generating section of your homology is given by this expression over here. So if you write it in, well, by making, well, let's say the generator of the Berezinian explicit, you get something like this. Okay, so you see that this expression is actually made out of all the anti-commuting section that you have, all of the anti-commuting generating section that you have in your, well, let's say in the full framework of the integral forms, because all of these are anti-commuting, all of these are anti-commuting. These are all the thetas which are anti-commuting, and these again are actually anti-commuting. So, okay, now I'm saying something that I would like to go through something that I can't really understand, but I don't know, maybe it might be.
I have a question here.
Sure.
Because I really have a hard time. You see, you're writing H0 of sigma p minus bullet, right? And this is generated by a section that doesn't change depending on the bullet. So p, p minus 1, p minus 2, it's always the same section as 0.
Sorry?
That's weird.
Sorry.
You're saying that H0, right, is generated by a section which has a certain expression.
Yeah, it is actually generated over K.
Okay.
So I'm not moving inside the, well, say inside the sheaf sigma. the complex of shift sigma, but I basically should imagine that I have a, well, I can only choose a constant over here. So I can only multiply this S0 by a constant over here. That's why I'm getting the sheaf of
you're getting the same no matter what. Sigma can be P minus 1, P minus 2,
yeah.
P minus 3. You don't change that.
I'm, well, if you look at this, you see that I'm in, well, 0, because I have actually chosen the grading in a certain way to be inside this H0. Different grading can be chosen, so I can be in well in the degree P, but I think that it's actually better to choose the grading in this way. So I'm in well, let's say degree 0 here. So I have some similarity with the ordinary Poincaré lemma for differential form.
Okay.
Well, you can say that this is a little bit, well, maybe not natural because, well, here I have a P, well, let's say a polyvector field of degree P, but the grading has been chosen so that this is actually leading me in H0. Just to have, well, let's say a similarity.
Yes, a bit mysterious this point, but okay, I don't have to.
I mean, it's just a matter of choosing the degree. I mean, you can shift the degree as you wish. I mean, it's not important, but I think that in some sense, also from the point of view of, well, for example, of picture changing operators, which are used by Carlo, Antonio, and other people, so, you know, Castellani. It is actually useful to have this appearing in degree 0. And I'm going to show you something now, which is actually related to this. So let us assume something which is not completely true, actually, which is not true. So let us assume that I can actually unpack this Berezinian over here, which is a cohomology class, so has to allow me to use the action of the D module M. So I have something like this, and I can use the D module structure of this operator over here to soak up all these thetas over here, okay? So if I do that, and basically I get this plus other pieces, which comes from the commutator of the D module operation, okay? But if I have this, well, if you allow me once again to use the duality pairing between these guys and these guys, and I recall you that these guys are truly the dual of these guys, I get 1 plus other pieces, okay? So this actually, well, let's say this relates in a sense the, well, let's say the generator of the homology, let's say the generator of the homology, the Poincaré lemma for integral form, with the generator of the homology in the Poincaré lemma for differential form. So you can tell that in some sense, this is really a sort of a, let's say, a sort of a picture changing operation. So how about other pieces inside here? Okay. The other pieces can be, in some sense, interpreted as sort of a pseudoform. So pseudoform are some, say, some objects, some forms which are related to more general sub-supermanifold of non-null codimension in the fermionic direction. So for example, inside these other PCs, I would get, for example, an expression like this. But you see that an expression like this, well, let's say an expression like this is nothing but the generator, once again, what comes out of the Poincare lemma for integral form for a supermanifold which has one less fermionic dimension, because you have only theta q minus 1, theta q minus 1 over here. Okay, so well, this is just this is just something that I would like to show, but I have no well, first of all, I'm not fully convinced about this, and I also have no interpretation for this. But I don't know. I mean, I think that it's good to, well, discuss on things. So it might be worth to show you something like this.
Sorry, Simone.
Yeah.
The problem here with the pseudo forms is that you unpacked the expression of S0, isn't it?
Yeah, exactly. So, you know, a problem that I see here is that somehow, you know, the illegal thing that I'm doing over here is that I'm unpacking basically the Berzinian. So I'm actually unpacking the Berzinian, and I'm basically working as, instead of really having, well, let's say an homology class, which has a meaning, you know, as an homology class, I allow myself to act with these guys, which stays into a certain, well, stays into the D module on this guy over here. But this is, well, this is not legal, let's say. So if I would be allowed to do something like that, well, the thing might be interesting in a sense, but I'm not sure how to interpret this. I'm actually not sure how to say about this. How to I mean, I'm not sure how confident should I be about say something like this. But you know, I think it's good to, you know, propose something and actually discuss about it.
Okay, and another quick question.
Yeah.
The fact that you don't find pseudo forms in the calculation of the homology is related to the fact, it is a question, is related to the fact that you do not have any special space, for example, the O space or the Berzinian space among pseudo forms?
I would say that is related to the fact that in order to find such a I would say that it might be related to the fact that in order to, you know, find a pseudo form out of a computation of homology or something like that, I should go for some sort of a choices, which basically is exactly what I'm trying to avoid in the construction. So if I allow myself to, you know, pick up some direction or something like that, well, maybe one can find something like that. But the point is that it is actually quite hard to think about an invariant operator if you make some choices.
Yeah,
so
okay.
This is the problem that I see in some sense. I would say that one way or another, like pseudoform might emerge by choosing some sort of a substructure inside of your supermanifold, or by making some choices in some sense. This is, I mean, this is my feeling.
Oh, because in the moment you make a choice, in some sense, you are again selecting a special space.
Exactly.
For example, that would be the space of integral forms on the substructure.
Exactly. So
Okay.
yeah, exactly. And well, for example, let's say this guy over here, from this point of view, it is exactly the thing that you said.
Okay.
It is well, let's say an integral form on a substructure.
Okay.
So it is exactly that.
Okay,
So
thanks.
you're welcome. All right. So oh, it's very late. Sorry about that. Just to briefly conclude. So we also happen to have a triple complex. So triple complex is nothing, too weird. Actually, is made out of the double complex, just taking the check cochains of the sheaves that I have, and I have another operator which clearly actually commutes with the other one, which is just the check differential, which is the first one here. Okay, and I can use this triple complex to prove, and it's actually very easy at this point, to prove that the invariant that integral form and differential forms compute for a supermanifold is really the well, let's say the RAM cohomology of the supermanifold, which actually coincide with the RAM cohomology of the underlying the reduced space of the supermanifold. So I have something like this. This is a, well, let's say this is a purely combinatorial object, which by the RAM isomorphism is actually isomorphic to this. And in turns, this is also isomorphic to the cohomology of the integral form. And it's actually very easy to prove, something like this. Okay, I don't really want to abuse your attention, so I would actually stop here.
Okay, so are there questions? That was very exciting, but in the end, I must confess, all the complexes took a toll. But are there questions? So Antonio, you were asking a lot of things before. Now it's time. Go.
So yeah, we can go back there.
So I have a question. What is this S0? So I don't understand what is S0.
Where? Sorry.
The S0, the last things that you.
Oh, sorry. Okay.
Me too. I have that question too. Yes. Go back. Go back. Yeah. Back.
Okay. So where?
Back.
Where was the S0?
Some slides back.
Okay. It's this guy.
Yeah.
Okay. This is the, well, let's say the generator, let's say the representative better of this cohomology. It's basically is the generator of this guy. And the only freedom that you have, and this is why you get this sheaf Km, is to multiply this by a certain like a real number or a complex number here, and yeah, that's it. And you can tell that this is a well, let's say this is an integral form of degree p minus p. So it is an integral form of degree 0 because you have a p polyvector field here. If you want a p polyvector field multiplied by a function, but p polyvector fields are an O module. So this does not really count.
Okay, so this S0 is the picture change operator. S0.
Yeah, exactly.
This is the product of the picture change.
Exactly. This was the point that I would like to make.
No, then I don't understand. Why is the picture changing? I don't get it. Why?
Yeah. If you write this object, I mean, if you these pi dx are the contractions essentially, okay, and the Berezinian dx contains the differential forms. So then, if you do the contraction, yeah, this is corresponds to picture change operator.
Okay, so to see the picture changing operator, you have to contract the axis and the
okay, you have to do something. Okay.
Yeah.
Okay.
See, you know, the difference in the differences in the say in the two point of view is that exactly like from one point of view. So well, you look at forms and contraction, while here I'm looking these guys at polyvector fields.
Yeah, okay, but this actually, these theorems is that what I proved with Roberto Matessi and Bernardi. Okay,
Yeah,
that
I mean,
is just the picture change operators.
Yeah. I mean,
I think Antonio, that if you wanted to give more detail on this next time, we would be delighted. Personally, I would find it very interesting.
Well, you know, my point of this is just that, I mean, as I said, this is a, let's say, a semantic point of view in a sense, which is dictated by some issue of naturality. So the point is to use you know, some sheaf that I can control in a sense, and yeah, like to, you know, find some agreement with say different formalism, which, well, it's clearly, well, it's really incredibly effective, which is the with the deltas and stuff, right? But this is
this actually, this expression is written like theta 1, theta 1, theta
exactly.
times the contraction along the
exactly
fields times VBB times the delta of size.
Yeah. This is exactly. This is precisely what you would be calling the picture changing operator. And the computation that I made here.
Well, it is the product of the picture change operator.
Exactly.
The Y.
All the picture changing operator.
The Y's.
Y's, exactly. And this computation, this well, let's say this, I don't even know how to call it, but anyways, something like this would be some sort of an effort to understand what's going on and to, well, say connect this as 0 with 1, which is, well, say the what actually came out of the Poincaré lemma for ordinary differential form, right? So you need to have a relation between these two things, between, like, well, let's say, you know, picture 0 and picture Q.
Well, I don't think that this calculation makes sense, but I think that I agree with you that S naught is the product of the picture change operators. Okay.
Yeah. From exactly. From it is in the formalism that I've given. It is what you would be calling the product of all the picture changing operator. It is exactly that.
All right. So
I would have written in a different way, but okay. So essentially, I have like thetas, then the contractions acting on the V's, okay, and delta of size.
Yes, of course, but I mean, the point is that clearly in this formula is there are no deltas.
Well, okay, you don't call it deltas, but
exactly.
Okay.
All right. So I think we want to thank you. It was great, but I must say personally that if Antonio is willing to say more about this next time, I would be really happy. So Antonio, what do you say?
Yeah, I don't know. Well, either I can translate into, let's say, a language that I understand, what actually Simone was saying. I can do that. Well, if you like. So
that would be great.
Yeah, because I think I'm speaking for everybody. I mean, Simone, you delivered a very nice lecture, but in the end, you kind of lost me because of all these complexes that were around.
I'm sorry about that.
No, but you realized there was a lot in the end.
Yeah, sure. Yeah, I can tell. I mean, as I said, when I give a talk, I'm pretty much interested into pass some ideas, and pretty much the idea that I would like to convey here was that you have let's say a shift theoretic point of view and an invariant point of view, which allows you in some sense to relate this differential and integral form and realize easily that these guys actually compute the same invariant for a supermanifold. And I mean, all these things, this, well, let's say this research has been actually prompted by, well, let's say by my encounter with Antonio and Roberto.
Yes.
So yeah, it is a sort of a, it is an effort of an interpretation of a formalism from a, well, let's say an invariant homological point of view. It's just this. So my point of view is, okay, I don't quite understand why mathematically the, well, say, how does it work, the cohomology of integral form? So this is a way that I have to, understand it. That's it.
So it seems
okay. Let's do it this way. Okay. Next time I can make a translation, and let's say like a poor-minded person. I am actually a version for a poor-minded person. Okay, integral forms for idiots. Okay, so I can.
No, but I love it actually. This is my point of view, Antonio. So it'll be perfect.
Okay. So you can make a title. Integral formula for dummies. Okay,
that's perfect. Okay,
but I don't.
And then I will translate all what actually Simone said in this language for dummies. I mean,
that sounds a great plan to me.
But yes. I don't quite. I mean, this might make me sound like pompous and pretentious. I don't
actually make it let's say the rigorous stuff. I will make it let's say the
dirty stuff.
Right, the dirty stuff. That's right. The dirty stuff.
Right. So it will be next week, Friday, right. But we can anticipate have it at 4, right? Because John, can you make it at 4, or would that be a problem? John was the one.
I think that's okay. Yeah.
Marianne, 4 was okay for you because I remember you.
Yes.
Okay, so that.
No problem. Friday, no problem.
Yeah. So also you, Simone, right? 4 is okay.
Yeah. For me, it's totally cool. I might be on 2 meetings at the same time, so I'm not sure I can.
Then it's not totally cool. Excuse me. That's really
no,
the definition of not cool.
No,
but
I mean, it makes no difference because, like, I'm having a meeting all Friday afternoon, so
I see.
It's okay.
So actually, you are in meeting.
Yeah.
So, all right, guys. So can I remind Simone to upload your notes?
I can. Yeah. Okay, I'll add some details to the notes, yes. So maybe they're gonna be a little bit more clear.
Okay.
And I have to upload it myself or I have to send it over to you.
I don't know. Maybe Carlo can help you. I forget where it is. What is the privilege if you can do it or not. Carlo, do you know this?
Okay, I'm looking for this.
Give to Simone the
all right.
Okay.
the permission.
All right.
Okay.
All right. We can coordinate among us. Okay.
Okay.